In this section, we're going to talk about something called a basis. So as you see here, the word bases is the plural form, and basis is the singular form. And so a basis is just a shorthand representation for a subspace or a vector space. So here is why a basis is useful. As we mentioned previously, it is a shorthand representation of a subspace or a vector space. It is a finite set of vectors. So there are only a few vectors in the set, and that finite set of vectors spans the complete subspace. It has one more property that we'll talk about in just a moment. So all the vectors in a subspace can be generated by the vectors in the basis. So here's the formal definition for a basis. It says, let S be a subspace of a vector space V, then B, right, so this thing called B, is a basis for S if it has the following two properties. We already mentioned this one, that the set of vectors spans the subspace, and the second one is that the set is a linearly independent set. As part of your reading assignment, I would like for you to write the formal definition for what it means for a set of vectors to be linearly dependent and what it means for a set of vectors to span. Some vector spaces have what is known as a standard basis. So for example, if we look at the standard basis for Rn, then it is simply the columns of the n by n identity matrix. Right? So that's the one that has ones along the diagonals and zeros everywhere else. Right? So the n by n identity matrix, or the columns of the n by n identity matrix, which form the standard basis for Rn. We also have a standard basis for the set of polynomials P sub n. Notice that those are made up of 1x, x squared, all the way up to x to the n. So if we were thinking about the standard basis for, let's say, R2, then the standard basis for R2 would contain the columns of the 2 by 2 identity. So it contains the vectors 1, 0 and 0, 1. If we were thinking about P2, then the standard basis for P2 would be the set of vectors that make up any quadratic polynomial, which would include 1, x, and x squared. As we just mentioned, the standard basis for P2 is the set of vectors that contains 1, x, and x squared. What we have represented here is a different basis for P2, and so we want to show that this set of vectors, or polynomials, which contains 1 plus x minus 1 plus x and x squared, is also a basis for P2. So it is a basis, but it just isn't the standard basis. So to show that it's a basis, we have to show first that the set is linearly independent. So set is linearly independent. And second, we must show that it spans P2. So what it means that it spans P2 is that if I take this set of polynomials, I can generate any polynomial or create any polynomial that is second degree. To show that this set of polynomials is linearly independent, we go back to the definition of linear independence, which says that if I take a linear combination of the vectors and place them in the homogeneous equation, so that's what we have here. Notice that I've just taken a linear combination, so I've taken constants and multiplied them by each of the vectors and ended up with the following homogeneous equation. We have to show that this equation has only the trivial solution. So only the trivial solution means that the only way for us to get 0, or the 0 polynomial on the right-hand side, which you see here, is for A0, A1, and A2 to be identically 0 with no other possibilities. Here is one way to show that B is a linearly independent set. So as mentioned before, we take a linear combination of the vectors in the set, which you see in the first line. And now all I've done is distributed the values of the coefficients through the equation, which you see in the second part. And now I've grouped together the like terms. That is, all terms that are constant terms, I've grouped those together. All the terms that go with x have been grouped together. And then, of course, x squared. And you get this third line. So now if I match coefficients, so what does that mean? I have a polynomial on the left-hand side. And I need for the polynomial on the left to be equivalent to this zero polynomial on the right. So it simply means that their coefficients have to be equal. So if we think about that, it must mean that this constant term matches to the 0 here. A0 plus A1, which is the x term, must match the 0 coefficient there. And A2 must match the 0 coefficient that goes with the x squared term. So when I do that, I end up with the following linear system for the coefficients of the polynomial. Notice that automatically from here we see that A2 is equal to 0. So we have one value. Again, to be linearly independent, we have to show that all of them must be zeros. From this equation right here, we have that A sub 0 is equal to A1. And then from our second equation, if we replace A0 with A1, we have 2A1 equal to 0, which implies that A1 is also 0. And since A1 is 0, that means A sub 0 is 0, so it tells us that all of the coefficients are zeros. Another way that we could deal with this idea of this set of vectors or polynomials being linearly independent is to recognize that P2 is isomorphic to R3. Now, what isomorphic means is that polynomials in P2 can be represented as vectors in R3. Right? That's what makes our isomorphism. So for example, if you look at the first polynomial expression, which is 1 plus x, how do we represent that as a vector in R3? Well, remember, these are supposed to represent quadratic polynomials. So the first term represents the coefficient for the constant, the second term in the vector represents the coefficient in front of x, and the last term represents the coefficient in front of x squared. So if we're dealing with 1 plus x, then the corresponding coefficients would be 1, 1, 0. For minus 1 plus x, it's minus 1, 1, 0. And for x squared is 0, 0, 1. So to show that B is linearly independent is the same thing as showing that these vectors in R3 are linearly independent. Of course, when we're dealing with showing that a set of vectors is linearly independent, all we need to do is put them into a matrix, and we're calling that matrix in this case A, and then show that each column of A has a pivot. So if each column of A has a pivot, that implies that AX equal to 0 has only the trivial solution because the solution would be unique. So we've taken the vectors or polynomials and placed them into the columns of A and reduced that into row echelon form, and notice that each column is a pivot column, which implies that the set is linearly independent. The second property we must show is that the set of vectors in B spans P2. To show that the set of vectors in B spans P2, again we take a linear combination of those vectors, and then we set it equal to an arbitrary quadratic polynomial, which is ax squared plus bx plus c. So here I've again grouped the like terms, and then for these polynomials to be equivalent, the the constant term must be equivalent to A, the x term must be equivalent to B, the coefficient B, and the x squared term must be equivalent to C. So you end up with the linear system that you see here. And we can actually write that linear system as an augmented matrix and put it into row echelon form. And notice that there's a pivot in every column of the matrix A, which tells us that no matter what is on the right-hand side, we're going to have a solution. Hence, we can say that B, or the vectors in B, span P2. Of course, we could have achieved this exact same result if we had recognized that this set of polynomials is isomorphic to vectors in R3, and then we augment that set of vectors with an arbitrary vector in R3, which contains B1, B2. And then, of course, we must show that this augmented matrix that represents the linear system AX equal to B has a solution for every B in R3, and we can do that by simply showing that every column of A again has a pivot, which again means that it does not matter what is on the right-hand side of this equation. Hence, again, just by creating that isomorphism, we automatically get the exact same linear system that we got previously. For the remainder of your reading assignment, I would like for you first to write the formal definition for a basis, and then I want you to look at this set of vectors in R2 and show that this set of vectors forms a basis for R2. So first you need to show, right, so it's a basis for R2. First you need to show that B is a linearly independent set, and then you need to show that B spans R2.